Welcome to ACS Webinars, bringing you the best and brightest minds in chemistry, live every Thursday at 2 p.m. Eastern. To view our upcoming schedule, please visit acs.org/acswebinars.
Today we're going to be listening to a presentation about how green chemistry can be used to turn waste into valuable products. We have 4 experts from the Green Chemistry Center of Excellence at the University of York. One of those is Professor James Clark. He's the director there of the Green Chemistry Center, where he has a large team of 80+ people who research biorenewables, waste valorization, and sustainable chemistry. Our second presenter is Dr. Avtar Mataru. He's the deputy director of the center, and he's the scientific leader for renewable materials platforms and technologies. Dr. Andy Hunt is the scientific leader of the platform for natural solvent technology selection, and Lucy Falsgraf is a PhD student under the supervision of Professor Clark. So now I'm turning it over to our presenters for their insightful and thoughtful presentation.
Hello everybody from the Green Chemistry Center of Excellence here in our beautiful city of York in the north of England, where we are all working together in the quest for green and sustainable chemistry. We have a wide range of activities in the center, as you heard, with over 80 people working on many different projects, many in collaboration with industry, looking in particular at how we can actually take waste and valorize that waste to make products using green chemistry methods. We're driven by the essential importance of chemicals and chemistry everywhere we look. So all the articles of today's society rely on chemicals and the chemistry that goes behind those. But we all know in green chemistry that every one of those articles presents a great challenge for us in terms of the way that we can actually make those articles, the way that we can handle the articles in our use, and also in terms of the fate of those articles thereafter. So everyone presents a challenge with regards to the resources, with regards to the manufacturing, and with regards to the end-of-life issues. And we also realize increasingly these days that we're very resource dependent. In the early days of green chemistry back in the 90s, there was a big motivation towards waste reduction, towards cleaning the process, towards using safer reagents, and so on. But what we've seen in the last decade really has been a recognition that we are facing a massive problem with regard to the availability of resources into the future. And one way of looking at this is to look at the periodic table in terms of the elements that we use in so many of those different articles and how they're running out. Now, this is something which my colleague, Dr. Hunt, Andy Hunt, will talk more about in a short while. Elements are in fact reducing very quickly. And this is because really we have been using all of these articles in a way that actually we might describe as a linear economy approach. We've taken the elements, we've processed them, we've turned them into articles like a mobile phone or like indeed a piece of plastic or anything around us. We've then actually at the end of the life of that article thrown it away. And most of those articles end up in a landfill site, and then of course it gets very difficult to recover the value. This is the traditional linear approach, which we argue is unsustainable. So this has been our challenge. And in a way, we've been thinking, well, really, this is really taking the two combined problems of waste and resource and thinking about how they can be combined together. At the moment, just to give you an idea as to how we currently handle our waste, we don't really handle it well at all. We have a very limited amount of waste management, and across the different countries, so here we've got data for the European Union and also for the United States and Japan. It's quite difficult to get that data for other countries. If other people can help us with that, we'd be very grateful. But here you can see the amount of their landfill that goes on. Most of the countries shown there, the bulk of their waste goes into landfill. There are relatively few countries which actually take that waste and use it in different ways. So composting gets some value back again. Incineration may get some value back in the form of energy if it's done carefully. And the recycle box looks quite promising, although in fact when you analyze what recycling actually means, it doesn't necessarily follow that we get much value back again. So we are not very clever in the way that we handle our waste. Now, as I said before, we believe waste in a way is a solution to the resource problem, because if we want to move from a linear towards a more circular economy, the challenge is, can we start thinking about the waste from a process or product that we no longer want for that particular application? Can we think about that as a resource to actually make other products from it? So our view at the moment is to say, look, all these different types of waste, these very interesting wastes, food waste, forestry waste, paper, municipal waste, electronic waste, all represent great opportunities in terms of the chemical and material potential they represent. So it's very much a sort of a mantra we have here, which is waste can become tomorrow's resource. Now, for the benefit of this webinar, and to give us some focus, we decided we'd talk about food waste and about e-waste in particular. And I just wanted to sort of get the ball rolling by just saying a little bit about food waste before we move on to metal waste, and then later on we'll come back to food waste with a case study. So if we think about food waste, we can actually start to see where the food waste is and how much is there. One of the most important aspects of any type of waste is to see exactly how much is there, where is it, and of course is it accessible. So we've been mapping food waste to coincide with the 2014, this year in fact is the European Year of Food Waste as voted by the European Parliament, and as part of that activity and part of a major network, we're now coordinating across Europe and even beyond Europe in terms of food waste and how we can use food waste. We've been mapping the amounts of food waste around the world. Again, we'd very much welcome people who might like to work with us on this and help us to identify and maybe firm up on some of the details here with regards to the type of waste available. But the map we're actually working on goes much beyond this, and for Europe, for example, where we have lots of data, we'll have a clickable map whereby you can actually go into a country and it will identify the major types of food waste available, or you can click on a type of food waste and it will show you where in Europe that waste is available. We'd love to extend that into the rest of the world. But it begins to give you an idea about the volume of waste available and where it is. And another way of looking at it is from the UN. The UN has shown that there is over 1 billion tons of edible food waste, and there's probably about 2 to 3 billion tons of inedible food waste as well, all of which has great chemical potential, as we can see from the next slide, which basically identifies the major components in food supply chain residues. And we know using green chemistry how we can extract those key intermediate compounds, and then using the methods of green chemistry to go downstream, to go to higher value, using clean synthesis methods, using technologies such as catalysis, we can make an enormous range of different types of products, which of course are essential to so many of those articles that we showed before. So we think the potential for this is enormous and yet to be fully realized. Okay, so let's carry on with the discussion now, and I'll hand over to my colleague Avtar Matri, who's going to speak next.
Welcome to the first case study on e-waste, and in particular liquid crystal displays. You're probably watching this webinar on an LCD, or liquid crystal display screen. Now LCDs are a modern day technological marvel because they're flat panel, lightweight and portable, unlike the clunky devices of my generation, namely cathode ray tubes or CRTs. In fact, the ubiquitous use of mobile phones seen today owes itself to liquid crystal technology developed way back in 1972. Today, the success of liquid crystals is phenomenal, with sales revenues topping over 100 billion US dollars. LCD TV is the largest area of growth. In fact, you can't buy a CRT monitor in many developed countries. So now here's a really outrageous statement. There are more LCDs in the Western world than there are people. Crazy, but probably true. Now let's pause for thought. I bet you're watching this webinar, you're listening in to this webinar, I bet you have at least 2 of the following LCD devices: calculator, mobile phone, portable handheld game, satellite navigation system, and laptop computer, all of which are based on LCDs. Hopefully you're now convinced that there are more LCDs in the Western world than there are people. So the tremendous success of LCDs is now leading to a techno-environmental problem, as more and more LCDs are entering the electronic or e-waste stream. Now LCD waste is the fastest growing e-waste stream in the European Union, increasing at an alarming rate of 15 to 20% every 5 years. Now luckily there is legislation in Europe which is known as the WE Directive, which addresses the potential harmful effects of LCD waste. And note I simply say potential. Okay, there is a huge problem that we need to address. The WE directive stands for Waste Electrical and Electronic Equipment, and the directive applies to LCDs that are greater or larger than 100 square centimetres, and those which contain mercury backlights. Okay, so small devices such as calculators and watches aren't under the WE directive. The mercury backlights are the most hazardous part of a display, and they must be removed. But once they've been removed, the display thereafter can be shredded or incinerated. Now that's outrageous, okay, because an LCD is resource rich, containing specialist organic molecules, the liquid crystal, which I'll talk a bit more about in a moment, the plastics, and indium, okay, an identified critical element that my colleague Dr. Hunt will talk more about. So what are liquid crystals? What's this magical material that we're all throwing away? Liquid crystals are essentially non to moderately polar organic compounds comprising carbon, hydrogen, oxygen, okay, and more fluorine. Liquid crystals, by definition, are compounds that exhibit an intermediate state of matter that exists between the crystal and liquid states. Hence the name liquid crystal. Now the synthesis of liquid crystals, well, it's multi-stage. It involves many toxic reagents. It involves low temperature, minus 80 degrees centigrade here in the UK and the European Union. I think it equates to minus 112 degrees Fahrenheit in the US. It involves precious metal catalysts, for example palladium, and processes that generate more waste than product. A really ludicrous situation. So the current practice for liquid crystal displays is to remove the mercury lamp. The liquid crystal, these organic molecules, okay, are actually classified as non-hazardous. So once the mercury lamp has been removed, the display can be sent to landfill or it can be incinerated. And again, we have a truly outrageous situation, because if sent for incineration, then we've got potential for fluorocarbon emission, and if landfilled, the liquid crystal, although deemed non-hazardous, persists in the environment as a sticky, greasy-like material that doesn't degrade, nor does it mix with water. Just imagine that lingering, being persistent in the environment. So we were tasked by the UK government to look at the recovery of liquid crystals from waste liquid crystal displays. Now just pause for thought again. If you have a broken LCD monitor at home, then be inquisitive as scientists. Okay? Open it up layer by layer to see the volume of rich resource that it contains. Okay? Our interest was to remove the liquid crystal and analyze it and look for potential reuse. Okay? So on the diagram that you're seeing, our aim is to follow the yellow boxes all the way through to the liquid crystal. Now at this stage, you're probably thinking, why am I seeing a cup of coffee on the screen? You know, is it just academic nature? You know, we all sort of drink tea and coffee all day long. Well, no, the cup of coffee, okay, if you drink decaffeinated coffee, then your coffee has probably been decaffeinated using supercritical carbon dioxide. It's a benign and environmentally friendly solvent. Supercritical CO2 has high diffusivity and preference for non to moderately polar organic compounds. So it's ideal for liquid crystals and coffee. Okay. So the next slide, this shows a schematic of our laboratory supercritical carbon dioxide reactor. Okay. Waste LCDs are shown by number 1 in red, marked on the left-hand side, okay, which are then placed into the extractor, okay, which is labelled 2. Supercritical CO2 removes liquid crystals, shown in yellow, into the separator marked 3. The system is then depressurized and the carbon dioxide is reused, invoking a closed-loop system. Okay. The liquid crystal that's isolated is shown in the round bottom flask on your right-hand side, marked 4. Now, as chemists, obviously we've analysed the material, and from our extensive knowledge of liquid crystals, we've identified several key important compounds which are otherwise very, very difficult to synthesize from virgin starting materials. So we've upscaled our process to handle 30 to 50 kilos of waste liquid crystal displays per batch, for which we were awarded the Rushlight Award for Technological Innovation in 2008. So we've got a proof of principle, proof of concept system that recycles waste liquid crystal displays. Now finally, okay, always remember, it's very easy and probably expensive to divert waste from A to B under the guise of remediation. The true skill is in making reuse of your recovered material. This animation shows the first example of a liquid crystal display made from waste LCDs, so waste LCD glass, waste polarizer, and the recovered liquid crystal from our supercritical CO2 extraction. The display works like a calculator, that when you switch it on, okay, a black digit appears on the screen. So, to sum up, through this concept of remediation, using green technology, supercritical carbon dioxide, we can make cheap, monotone displays that can empower the third world with communication and information technology from devices that would ultimately end up being incinerated or landfill. And that's how we create wealth from resource and invoke the concept of a circular economy.
Okay, so now thank you, Avatar. Let's move over now to our colleague, our author, Andy Hunt.
Thanks very much, James. So I'm going to talk very briefly a little bit about elemental sustainability. James touched on this subject in his earlier slides, but elemental sustainability is really the concept by where we ensure that every element in the periodic table is guaranteed, so we don't impair or restrict future generations' use of these elements. There's a very good book, if you want to read more on the subject, from the RSC that was recently published. So James has already showed this slide and spoken to us a little bit about many of the elements in the periodic table actually depleting, so the known reserves of these elements are actually running out. Avatar mentioned indium as a critical element. In actual fact, there are 13 years of known reserves of indium left in the ground. So we really need to think about recycling these materials. At the moment, what we're doing is we're taking them out of the ground, we're using them, and we're dispersing them through the technosphere. We're not actually destroying any of these elements. What we're doing is we're spreading it around the world and therefore making it much harder for us to recover and recycle. And when you look at the recycling of these elements, in actual fact, you can see that many of these elements have very, very poor recycling rates. One of the exceptions are the platinum group metals that are typically used in automotive catalysts, and they're recycled on a very large scale simply because there are good systems in place for recovery recycling. And those are normally through the garages that you take your car to be serviced or maintained. So there are good routes there for recovery of those elements. Many of the other elements that you see in the periodic table have very, very low recycling rates, and this is something we need to improve on, whether it be in terms of use in mobile phone applications, LCD panels, or even catalysts when you're conducting your chemical reactions. Also, many of these elements can be found in specific locations throughout the world. South Africa actually has about 95% of the world's platinum group metals. Recently, China has been producing about 90% of the world's rare earth elements. Now, it's fine if these elements are obviously shared around the world, but recently China have adopted issues or policies where they've used elements internally within their internal markets. Obviously, this has made the rest of the world look for new sources of these elements and also new ways that they can actually recover them. So I'm going to tell you a little bit about a case study that we've been working on here at the University of York. If you're interested in finding out more about this subject, we recently published a paper on this area. It is open access, so you will be able to look at it, and also the website address is PHYTOCAT.org. So PHYTOCAT is really a project that's designed to capture metals using phytoremediation, and this is to trap the metals in situ, and then we use the plants as catalysts. So we're kind of growing our own catalysts. And really what we're trying to do is we're trying to take waste mine tailings and use the plants to uptake those. In actual fact, what we've found is these plants can actually form nanoparticles within their leaves, and we're able to then use these in green chemical applications. So the work that we've been conducting, we've actually been using a model plant called Arabidopsis, and we've doped the plant with a palladium-based salt, and we've shown that over time, over 3, 9, 12 hours, we end up taking up the palladium into the plant. And you can see here in the micrograph on the bottom right-hand corner of your screen, in actual fact, we end up forming these very nice discrete nanoparticles that we then use for catalysis. What we do is we first stabilize the structure by heating to about 300 degrees, so we kind of carbonize or char the material, and then we use that as our catalyst. When we're doing our chemistry, in this case we've been doing some coupling reactions, some Suzuki reactions, and what we've seen, the palladium will dissociate off the surface of the support or of the plant. Coupling reactions will then proceed via a quasi-homogeneous phase, and then they will be redeposited back onto the surface of the support. We've shown that we're able to reuse the catalyst several times with very little decreasing in activity. However, after a number of recycles, what we end up seeing is the palladium being redeposited back on the surface, and preferentially on top of other nanoparticles. So we end up getting an agglomeration of nanoparticles. And you can see that in the nanoparticle diameter distribution here in the right-hand side of the picture. However, we have shown that these are very effective at catalyzing coupling reactions, as I mentioned. The Suzuki is one of the examples, and here are a number of substrates that we've actually used for this kind of chemistry. So this has been shown that plants can be effective for taking up metals from waste streams such as waste resources like mine tailings, and then can be used in terms of doing green chemistry.
Our next talk, which is from Lucy Falsgraf, and she's going to be talking about one of our most exciting case studies, the orange peel exploitation.
Good evening, everybody. I'll be presenting an example of use of waste produced by the food industry. In this case, I will be talking about why citrus peel. Fruits like oranges, lemons are commonly known as commodities now in the developed world. They're grown all around the globe, on both hemispheres, except that whenever they're juiced, 50% of the weight of an orange is actually wasted. In countries like Brazil, which is a huge producer of orange juice, it's even landfilled or burnt. Now, citrus peel contains very interesting chemicals such as D-limonene, flavonoids, pectin, cellulose, hemicellulose, and sugars. You can add also lignin. The percentage quoted here are all based on dry mass. What I'd like to show tonight is, or this afternoon for our American colleagues, how organic waste utilization can be worked out instead of organic waste production. I'm going to give a few words about microwave technology, which is a technology we're quite keen in York. You can see a picture of one of the pieces of equipment that we've got. It's 1 out of 5 or 6 now. So the desirables for the process and the use of microwaves in this case applies to citrus peel was microwave technology is a form of volumetric heating. It's scalable, used in industry, especially in the food industry, for sterilizing products or even drying purposes. It's flexible, allows continuous processing, which is very important in our case, being into sustainable chemistry. Feedstock agnostic. A microwave plant could be used to valorize different types of feedstocks. And it allows the use of wet feedstocks, which is very important here because when scaled up, being able to bypass the drying stage is really important. We extract 3 chemicals, the first of one being D-limonene, following a microwave-assisted steam distillation using the inherent water content in the peel. D-limonene can be used as a flavor and fragrance. It can replace halogenated compounds to decrease electronic components, and of course as a platform molecule. Then we reuse the peel that we've D-limonene extracted and then subjected to a Soxhlet extraction. Now I've put on here that we use acetone, but we've also used ethanol increasing by twofold the yields of flavonoids extracted. Those flavonoids are polymethoxyflavonoids and compounds such as hesperidine, which have a very broad spectrum of biological activity, antifungal, anti-cancer properties, but also antioxidants. And then we subject the peel to a hydrothermal microwave treatment for the extraction of pectin, which can be used for food application, but also as a drug substrate, for example. Just a few words about the different chemicals extracted and how they've been characterized. The delimonene phase has been analyzed using GCMS, and actually the presence of alpha-myrcene, alpha-pinene shows how our delimonene containing fraction has an interesting fragrance profile, which industry has deemed interesting. Here is a ESI spectrum showing the 4 polymethoxyflavonoids we're extracting using water and ethanol-based workup. We are working on their separation using supercritical CO2 chromatography. Here is an illustration of the application of pectin, where on the right you have commercial pectin and on the left you've got the pectin we're extracting, and they gel both at the same conditions used in industry. To wrap up my part of the talk, we've been developing a low temperature hydrothermal microwave process separating pectin from cellulose in the cell wall without any acid or other additives. The process releases pectin, delimonene, flavonoids, sugars, furans, and cellulose. It all has been done using food-grade accepted solvents such as ethanol and water. Delimonene and pectin meet standard quality requirements as assessed by an independent company. The process potentially could be run in one step, and this is something we're looking forward to develop with a company, and a techno-economic evaluation is currently underway.
Thank you, Lucy. Well, I hope that we've been able to use our talk today to actually help persuade you about the importance of moving away from the linear approach of actually using resources as though there was no limit and throwing away the articles at the end of their life without any consideration about recovery of the resources. We believe the circular economy is the future. We hope we've shown that there are technologies available to actually help extract the valuable resources present in such substances as food waste, metallic waste coming from e-waste. Many exciting technologies to allow us to go forward towards a true circular and sustainable economy. There is a lot of information available. Our main website you can check out. There's a lot of information there that links into various other places. There's also various YouTubes available that you can see more about what we're doing here at York and the things we believe in. And you can also follow us on Twitter. And there are a number of websites there representing some of the major networks and collaboration activities we have running at the moment.
Thank you for watching this presentation. ACS Webinars is provided as a service of the American Chemical Society as your chemistry source for live weekly discussions and presentations that connect you with subject matter experts and global thought leaders concerning today's relevant professional issues in the chemical sciences, management, and business.